Yeah, thank you so much. So it's a pleasure to be part of this webinar again and talk a little bit about measurement fundamentals of AC/DC switchboard power supplies. This presentation was initially prepared by my colleague, Gabriel Rojas, and I'll be your presenter today. So what will we be looking at? So some motivation words, then have a look at the AC/DC switchboard power supply basics, some input-output measurements that are popular, switching stage analysis, and then conclude everything with some final remarks. So what's the motivation? Basically, from a design perspective, first you'll have a definition of the architecture, you'll select the circuits, the design of the PCBs, you might do some simulations, and finally, we have to conclude with the testing. So we'll have to verify the sub-circuits, switching times of the transistors, also switching losses. We'll have to characterize the passive components. So if they are matching to the initially planned results, so meaning ripple, efficiency, and also the stability of the supply itself. Of course, efficiency overall is of interest, and at the end, also electromagnetic compatibility so that your SMPS is not causing too much interference in your whole setup. When we are looking about the new upcoming wide bandgap materials, we're seeing, okay, with silicon carbide, gallium nitride, switching frequencies increase, and also does the power density that could be achieved. And both will cause us some headaches. So the increased power integration density will mean we're also having to take care about how to get the heat dissipated from the switching devices when there are losses occurring. And also by having a higher switching frequency, we'll have to ensure that these are not causing us headaches in the other EMC bands. So that when we are doing investigations inside the EMC chamber. Basically, what's an AC/DC conversion needed for? Typically, we'll have an AC mains, and then we'll have some DC charged or supplied equipment at the end. So it doesn't matter if it's a battery, a cell, a computer, TV set. Basically, all of these have the same needs. So we're having the need for a DC supply at the end. Traditionally, we are using linear power supplies. So we'll have a transformer with a good old iron core inside. We'll have the diodes for rectification. And then at the end, we'll also have to ensure that ripple gets reduced. And therefore, we are having the circuitry next to that. Nowadays, to reduce the losses and also to shrink down the devices itself, we are no longer using iron cores at the input stage. We are adding an input filter. We are having the diodes, and we'll have our switching converter here at the switching stage. Inside, we are doing then more or less a switching between high and low. And at the end, we also have some filter networks needed. And most commonly, we'll have these LSC tanks at the output and a regulation load. So we have a target load and we'll have a feedback loop, which controls, again, the switching of the devices to ensure we are meeting the voltage and the current at the output. For power supplies with a certain amount of power, you're mandatorily forced to have a PFC, so an active power factor correction inside. And this shall ensure that you're having a phase match between current and voltage and thus reduce the losses. So also the losses on the AC mains, meaning that we are not consuming an excessive amount of blind power at the power supply itself. Different modes of operation here for the PFC converter. So you could have a fixed frequency average current mode, or you could have the transition mode. This is more or less important to know how this operates if you'd like to go for the further debugging and analysis in the circuitry. In general, it all depends on the calculation power you're willing and able to spend there. So if you're taking the one or other thing first, and then of course also for the overall efficiency settings. Which measurements are of interest? So we have some input, and at the input for an AC-DC or DC-DC converter, we'll have to ensure that a certain amount of harmonics is not exceeded, also the power quality matches the needs, and how this converter handles the inrush current behavior. At the output, we'll have a ripple, load transient, load regulation, and overall, when doing the input-output characteristic measurements, we'd like to have an overall efficiency, power up, and also power down sequencing. Let's start with the input characteristics. When we're looking at the power quality, so first of all, the power factor correction shall ensure, as mentioned already, that our current and voltage are not having a certain phase shift, so we are only consuming more or less resistive-like power consumption here. And this helps us to save energy costs because we don't have to pay someone to provide this blind energy to us. Also, efficiency is increased, and we can reduce the components inside our supply, so we don't have to add additional caps or inductors. And that's why it's very helpful to take care about this phase shift in between. What's behind? In general, all we are consuming is the apparent power, and if we are lucky, we are only having reactive power, only having real power, and we'd like to avoid excessive consumption of the reactive power to not get the phase shift in between the voltage and current at the end. What's the power factor? Power factor means what's the relation between our real power and the overall consumed power, and this gives us at the end also the relation of the load itself. Crest factor, what does that mean? So we're having in an ideal case at the AC mains in sinusoidal waveform, and if we are taking the crest factor into account, this gives us a relation between the peak value, so the absolute maximum value, and the RMS value. So these typically 230 volts in Europe, or 110 volts in the US, to the square root of 2 as a maximum value. So if the crest factor delivers the square root of 2 as a result, you'll immediately know that's a perfectly sign. As soon as we are not getting a square root of 2 and this deviates, we'll see, okay, that we are having no longer a nicely shaped AC. So it's no longer a sine wave, and we'll have to take care how to clean that up to prevent the excitation of our switch mode power supply with these higher frequency components that will be hidden inside the signal, as well as to prevent the propagation from the input of the power supply to the output. Also, what we like to avoid is this flat topping, so that we are more or less only getting a rectangular signal instead of a AC signal to our switch mode power supply. Why are these input harmonics so harmful? If we'll think about the losses, higher frequency components will cause also higher losses due to the parasitic effects that might resonate inside these devices. Also, electromagnetic interference could be caused by these because they have a different propagation model. And if your filters are not designed correctly to prevent that, you might have a propagation from the input of the switch power supply to the output, and then you'll have an more or less other propagation path inside your system. Also, overheating could be caused, and that shall be prevented. For the PFC itself, also total harmonic distortion is a crucial parameter, and here we're just comparing the RMS values. For the output, we'd like to see how much ripple and, of course, other disturbances might be caused by the switching itself or by coupling from the input to the output of the switch mode power supply in the surrounding of our target output value. If we'll think about today's electronic systems, there's only one trend quite obvious. So more or less each of these active components we'd like to power up has its own preferred voltage. And this does not necessarily even have to be 1 volt. It could be even 300 millivolts, 500 millivolts, you name it. And thus also the tolerances, if you'll take that into account, lead to a real low voltage value that can be tolerated by the input of these active devices. So that's why it's very important to characterize these so-called parts, so periodic and random deviations around your DC supply line. We'll have there ripple, switching noise, load step, LC tank behavior, as well as random noise. Um, Noise is always a tough thing because noise shall be unbounded in the frequency domain, and also a slight hint for the definition. Typically, everything above 20 hertz is meant by this AC noise. Everything below is meant as output drift. So also here, please be cautious when doing these investigations. It might be that you'll see some thermal drift behavior, which will be low frequency effects, and everything above might more or less only be related to your switching inside the switch mode power supply. What's in with these transients? So if we are looking at the signal itself, that shall be our intended output voltage. Our ripple is always meant for this sinusoidal shaped behavior. And then we have on top these non-related switching transients. These could be in phase, out of phase to the sine wave, so they don't have to necessarily occur at the top or bottom. They can more or less occur at any position on the sine wave. The bad thing on these peaks is these are having steep edges. Steep edges mean they are inducing a wide frequency spectrum. And if your probing solution, we'll talk about later on, is insufficiently chosen, so you are having a lack of bandwidth in that case, you might be unable to see the full beauty of the peak, and thus you might have an underestimation in your pre-investigations before you go to a customer site doing measurements, maybe also at the EMI lab. And this could lead to some headaches when you see, okay, what's coming up there and where it's coming from. So it's very important to always think about what am I expecting inside my switch mode power supply as the steepest edges. And with this, you will get a definition of your needed bandwidth of your oscilloscope and probing solutions at the end. When doing investigations on power rails, of course, the most common one would be using a passive probe. So these 10x1 probes are typically delivered with any oscilloscope on the market. And if we'll do so, we'll have some pros and cons for this probing system. It's cheap, it's there, you could just connect it. But at the end, using a 10x1 probe always gives you a headache because this 10x1 probe gives an attenuation at the beginning of the probe head. So each voltage is attenuated by a factor of 10. And as the oscilloscope recognizes this 10x1 divider ratio, it's automatically multiplying every sampled voltage point internally with a factor of 10. So also the base noise of the instrument is magnified by a factor of 10. And if you look at today's oscilloscopes, typically you'll find in smaller vertical scales an input noise of about 1 millivolt peak to peak quite easily. And if you remember the previous table, but you shall qualify a ripple of up to 10 millivolt peak to peak. So 1 millivolt of noise multiplied with a factor of 10 would immediately cause you some issue because you would have then already 10 millivolts on screen, and then every additional peak would cause you a violation of your target. Additionally, DC blocks are quite commonly used to suppress the sampling of the DC offset. So for these probes, it could happen for the higher power voltage supplies that you will have an offset that is larger than the offset compensation can handle inside the oscilloscope. Then you would have to shift your measurement range from 5 millivolts maybe to 1 volt or 10 volt per division for being able to capture the DC offset. And thus you would reduce the number of bits of the ADC being available to capture your noise on your rail. So if you'd like to have any rail measured as flat as possible, just use a large enough input scale, then it looks flat. But if you're using a DC block, you run into another issue. So we've been talking about these low frequency deviations, and each DC block has a lower and an upper 3 dB corner frequency and input frequency range characteristic. And with this lower frequency cutoff point, we're adding attenuation to these lower frequencies, and thus these will be suppressed in the measurement result. So if you'd like to qualify frequencies below the lower frequency point, you would run into an issue because you will no longer be able to qualify these when activating AC coupling or adding the DC block. If you're having an external DC block, you might get at least a specification. Typically for oscilloscopes, the internal AC coupling is not specified, so you'll have no chance without using an external signal generator, performing a sweep, seeing when the sine wave you're entering there gives you the full amplitude again. But that would be additional effort. That's why typically we not recommend to use DC blocks if they can be avoided. There are also some one-by-one passive probes at the market. And for these, you'll have some drawbacks in the limited offset range. So same issue like the passive probe. If you're exceeding the input offset range of this probe, then you'll have to use ADC bits to sample the DC offset instead of sampling what you like to see, the ripple. But as it is a one-by-one probe, you immediately see the noise behavior is nicer because you see the noise is not magnified like for the 10x1 probe, but due to maybe limited bandwidth, so these probes typically go up to 30 or 40 megahertz in that range, you'll see that these peaks might occur, but they might already be low pass filtered. So also not the best solution, but it's a very convenient and price sensitive solution too. That's why for a certain while, these so-called power rail probes are available. The probe itself is a transimpedance converter, which is housed into this box here at the bottom. We'll have a coaxial cable, which could be connected to a solder in. So that's a coaxial cable where you'll have the center pin available and the ground connection, and then could easily solder that into your design at the certain test points. With this, you'll get bandwidths for the coupling bandwidths of 2 to 4 gigahertz and an offset range between 60, 70 volts, depending on the model. The cool thing is having an active amplifier inside. We're having a 1:1 attenuation ratio, and we are also able, with this high offset range, to use the full ADC range with full bandwidth of 2 or 4 gigahertz of the probe system to see what's happening. Just to give you also some background, why 2 or 4 gigahertz? It's not that we are expecting that your switch mode power supply will give you such high harmonics. It's more or less also a general purpose debugging tool. And if you think about this increased integration density, so you'll have more or less in every device nowadays a Bluetooth, wireless LAN, LTE, 5G modem, what else inside? And for being able to see these different bands and their relation and coupling on the power rails itself, it's very helpful to have this bandwidth. Otherwise, you wouldn't be able to characterize if there's a crosstalk or not. And you might see these high frequency components that could easily propagate through a rail to your system on chip, and then cause there a watchdog saying, oh, I'm out of spec here and I'd like to reboot. And this might be the cause by this unattenuated propagation inside the system. What else to keep in mind? So if we're having a switch mode power supply, it shall power something. And at the end, if we'll have a system on chip, FPGA, ASIC, doesn't matter, and it starts to do something or anything, it will consume some current that's shown here. So the currents could jump significantly between the different values. And the jump in the current will immediately cause a drop in the voltage. And you, as a design engineer, have to ensure that your power supply is able to provide that amount of charge to get the current out to the system, and thus avoid also this voltage drop. So at the beginning, it's quite normal. We're seeing some drop. Then we'll see then where regulation takes place and also feeds the charge back to the system. And the question always will be, is this now acceptable or not? And that's why also you'll have to know what will be the maximum and minimum charges you'll have to see inside your system, and thus also know the slew rates that would occur by drawing the current out of your switch mode power supply. For the load regulation, also it's important to calculate what's happening between no load and full load, and that you're not exceeding a certain output voltage range when drawing these different currents. When having measured the input and output characteristics, so we have ensured our AC source is not providing an excessive amount of high frequency energy to our DUT, which is the switch mode power supply. And also, thus, it is ensured that this cannot be propagated unintendedly to your load. Also, we have validated that the output power itself is okay, so the load step response is okay. We might be interested in qualifying the overall efficiency of our design, and there we'll need to measure the output voltage current as well as the input voltage current, and then ensure to do the maths here. In addition, we might not only watch at this for one working condition, also this is strongly depending on our load we are using there, and thus you'll typically get such many curves, so some in snooze mode, some with defined loads, and this gives you an immediate overview about the overall power consumption, which might be crucial if you'll design a small battery-powered IoT device, which shall only wake up every now and then. And then it's important to know how much current is drawn for which working condition to do a lifetime assumption of that battery. If we'd like to do these calculations of the consumed power properly, we'll always have to know if the current and the voltage are aligned properly. So both of these probes, independent if it's an active, passive probe, but all probes have a different group delay. So meaning we'll have to know the individual delay of these probes for being able to have a proper alignment between the voltage and current. And therefore, some example here shown. The colleagues once designed a so-called power DSQ fixture where you'll have the chance to connect your voltage probe, your current probe across the board. And due to the known relation between the current and the voltage at these two test points, you are now able to DSQ your system. Later on, in most cases, you will be not able to use such a fixture, but as you know, what kind of switching devices you will have in what kind of reactions will be happening when you'll have a certain load jump. You could align these different voltages and currents quite easily by, for example, searching for the Miller plateau when doing investigations inside the switch mode power supply, or by known characteristics of your design itself. So here it's very important to just keep in mind, you'll have to DSQ to do a proper efficiency calculation at the end. Otherwise, your efficiency might be lower of your device due to this effect that voltage and current are not in phase. Also, power up and power up sequencing plays a more and more important role nowadays. So what does that mean? At the beginning, we'll have to power up our board in a certain order. So first of all, the switch mode power supplies have to be ensure that they are turned on. They are giving the right voltage rails at the output, and maybe you'll have a power management IC, a so-called PMIC, in addition on your board, which then regulates the outputs and powers the different power supplies up in a certain manner that the DUT is coming up in a well-defined way and is not already transmitting or trying to transmit something while the backend is not running and so forth. And therefore, also, it's very important to know what will be the maximum inrush current I'm allowed to consume at the beginning of my chain of maybe different or many switch mode power supplies, and also which overshoots shall be achieved at a maximum. So this is a complete system behavior test. And typically you'll need not only one, two channels, You also need several of these different signals to correlate the system behavior. And then you're seeing, okay, what's coming here for a voltage, for the current consumed at the end, and do these match still the requirements that I've been given in the datasheet upfront? So a typical startup sequence is we're getting here the sine wave in the back, which already starts as maybe a clock. Then also other consumption at the bottom is shown for a certain voltage level. Ramp up takes place. And all these timings could then easily be measured using cursors, maybe automatic math functions, using maybe also gated measurement functions. So meaning you're adding different timing gates to do different measurements and see at the end if your supply and your system match quite well together, or if there are different hiccups coming up. So it might not take only 8 cycles, it takes maybe 8.5 or 9 cycles to get the reference voltage out of a certain switch power supply. And then you could start debugging in your design how to power up these different supplies and still ensure that you're not exceeding the maximum power consumption at the input port of the device, and also ensure that sufficient amount of power is always provided to your different parts of the design. For power down, it's more or less the same. So if we'd like to power down a device in a controlled manner, it's sometimes also needed that we'll first switch off in a certain order. So to avoid that we are getting overshoots, we are preventing also uncontrolled and maybe destructive and thus maybe destructive voltage overshoots inside your system. So if you think about an inductor and you'd like to cut off the power at such an inductor immediately, this would cause you a lot of ringing and headaches afterwards. What happened? And that's why it's very important to power down in a certain order to ensure that all power that has to be that you'll have to get rid of first is gone away, and thus it's unable to resonate in your system. What could be done when we'll know, okay, at least I'll have everything made that I was promising in my data sheet, but now still I'd like to go deeper in the switching stage. So first question would be, like always for selecting your measurement system, which bandwidth do I need? This strongly depends on the measurement equipment. So for the shown MX04 with an RTZHD high voltage differential probe, you could assume your bandwidth by this formula. So the needed bandwidth will be 0.35 divided by the rise time of your switch you'd like to investigate. And for this example, if we'll have a 4 nanosecond rise time, this would result into approximately 90 megahertz of frequency input range needed here. You'll find different of these formulas. So stating 1 divided by pi multiplied with the rise time, or you'll find 0.5 so, or 1 divided by 2 times the rise time. This always depends strongly on the input filter characteristic. So if you'll check the data sheet of your measurement system, so the probe as well as the scope, then you'll find the formulas and you could easily use them. If you'd like to do a much more easy and generic assumption, you could always take 0.5 divided by the rise time, because this will give you the most conservative estimation of the bandwidth needed. What shall be done? First of all, if we'd like to see our switching stage, we are switching between a certain low and high value. And there we are interested, first of all, in the slew rate, so that we are not too fast or too slow. Also, how large is the overshoot, ringing, and the differentiation between ringing and overshoot is quite easy. So ringing is something where you'll have a very consistent way. So you could draw a line over these amplitudes, and then this concludes to 0. While an overshoot has a very high peak and settles immediately afterwards. So that's a very easy thing to differentiate if this is maybe a ringing, so caused by some resonances inside the system, or if it is an overshoot, so maybe caused by some inductor or other system behavior. Also, a voltage drop might be of interest for you, so meaning what's the relation between the high value at the beginning and at the end of your measurement. If you're comparing the slew rates or maximum slew rates that could be measured and the rise times that could be measured with the given intrinsic rise times of your oscilloscope, please always be aware, oscilloscope is always specified to measure at 1090 value. If your definition of your DUT gives you a 2080, 2575, doesn't matter. This always means that you'll have to translate these other boundary conditions to your oscilloscope, which will give you a 1090 value. So you could assume that your linear range of the oscilloscope is then faster, because this 1090 value you could decrease to a 2575 or something like that. So that's just a linear scale, and then you'll get the values for 2575. In addition, it's very important to also be aware your software inside the oscilloscope will always, as a default value, give you in a rise time measurement the 10 to 90 values. If you're now having these other specifications and you like to reproduce some datasheet values of your colleagues, it's always important to adjust these settings in the firmware of the oscilloscope to do the measurements at the right positions here. And that's what's basically stated here. So please be aware if you're having 1090, 2080 values, also which voltages you'd like to measure. So gate source, drain source, and also that you shall not forget if you'd like to align high side, low side gates measurements. Also be aware that you'll have to, first of all, know the skew between the input channels. Maybe also know the skew of your adaptation from the measurement points to be able to really get to the tightest margins for your dead time analysis, so that you're ensuring that your high side and low side gate are not active at the same time. So meaning that you're not building a short circuit between high potential and ground. So basically, let's try getting to the robustness testing. And here again, a skew has to be considered between all the input channels, and that's a probe individual thing as well as channel individual thing. So if you're exchanging the probes between the channels, you'll have to start again to do the alignment and the disqueuing between the channels, because it's always a function of probe plus channel. And if you're exchanging the channel, of course, there's another number stated behind. Which measurements are very popular and what to keep in mind for current topologies and technologies. So if we're only investigating the lower gates and the low side transistors there, everything is ground referenced. That's quite convenient and easy, because there you'll always have a ground connection, and that's why it's more or less a don't care. You'll just take the voltage values and look into the datasheet of the probe and say, yes, that's good to go. As soon as we are talking about a high side gate measurement or a high side measurement in general, so high side VDS or VGS measurement, there we'll have the drawback that our source will not be connected to ground. This one will be connected to a floating potential. And especially for floating measurements, it's very important to know the common mode rejection of your probe. Because this will give you then the finite limitation for the measurement accuracy. So even if you're connecting the P and N port of your probe to the same testing point, which typically will be the floating potential at the source, you'll see some remaining voltage ripple coming up from the switching event from gate to source. And that's due to this limited common mode rejection ratio inside your system. On top of that, when investigating silicon carbide, gallium nitride gate drivers, typically these are floating too. So it's always depending on how high their isolation impedance against the environment and the ground itself is. And in dependency of this relation between the gate isolation and the isolation provided by the differential probe, you'll see more or less effects. So adding a high voltage differential probe without a galvanic isolation could cause you ringing effects at the gate source and might lead to destruction of your device, due to the parasitic couplings inside the probe. So that's why it's important to be aware. You not necessarily have to have issues here, but if you'd like to test if you really need a very expensive isolated probe, or if maybe the differential voltage probe would be okay, I always recommend to do these tests with the smallest possible current consumption of your device. So at the end, that you'll avoid destruction if you might get a short circuit by the gate characteristics here. What's important to know? So if we'd like to measure losses at the end, we'll have our drain source current, our voltage, and of course, the switching loss is determined immediately by multiplication of these two channels, so current and voltage. And as you already could imagine, I've mentioned we'll have a specific delay for each probe. And if we'd like to now do a proper power consumption calculation, we'll have to know if IDS comes more early or later, because this will immediately change the conduction losses and the switching losses. In addition, also the inductor current is sometimes quite tough to measure. So to see if your inductor is saturated, desaturated, or maybe also causing you some overvoltages you didn't expect there. The crucial thing here is to measure the inductor current properly, you'll have to change something in your system anyhow. So always be aware if you're measuring something, you might cause issues in your system. Especially if you'll go to the output of your inductor and you're adding a certain wire, this will change the effective inductance inside your measurement system, and thus you'll see different measurement results at the end. So that's what's shown on that slide. If you're using such a structure, you'll have your inductor plus the loop inductance where you're adding the probe. And typically, it's better to use a shunt resistor because it's less invasive than adding these long wires. But also here, you'll have to be aware if you have the need to qualify real small currents and also real high currents while having the negative path here, then your dynamic range will be limited by the proper selection of the shunt resistor as well as the probe that is measuring the voltage across this resistor. So as mentioned again, we will have some floating potential across the shunt. And through this floating potential, we might have a limitation in the effective ripple and also noise behavior later on. So also here, it could be a good idea to use an isolated probe to get rid of the offset voltage and use in as low as possible diode ratio, and thus increase your versatility in your measurement. This brings me to the end. So the final remarks. We've had a brief view about what's popular to measure for AC and DC-DC switch mode power supplies. There are many more measurements that are of interest for you if you're integrating and designing these different tests. So robustness was only touched briefly. Inrush current analysis has not been discussed in that detail. We'll have double pulse testing. And especially the double pulse could be of more interest in the future for you because double pulse does not necessarily force you to only qualify how is the behavior between the high side, low side gate. It could also be used to qualify the overall system behavior so that you're using a reference load to your complete system and then do the analysis on different switching patterns, different switching schemes, like we've seen previously from Florian's presentation with the spread spectrum clocking that might be used. And then you could also do an estimate already inside these test systems on the losses effectively and also the system behavior. In general, the parasitics are causing us the most headaches, and the higher the frequencies get, the more harmful are these parasitic effects. And that's also something we'll take care in the presentation of next week, how our measurement system is affected by these high frequency components and also how to get a good accuracy or at least a reproducible measurement out of our setup. A last remark, which I'm always emphasizing at the end of such presentations, today's oscilloscopes offer a very powerful FFT already inside. I guess you've already seen that at Florian's presentation, and also you'll see something on that in the presentation of Arturo. An oscilloscope has an FFT, and please use that because it's always good to be prepared if you're going to the EMI lab at the end or doing more enhanced analysis. Switch on the FFT. It takes about 5 to maybe 10 additional minutes on your setup at your desk, and you immediately see what's happening inside your system, which frequency components occur, and you are already better prepared to see also from which stages in your design these might be occurring if you'd like to hunt down the EMC issues. Also, there's a nice app note. You'll get the material afterwards, like we've already heard, and thus please be happy to download that one. It's very informative and also contains a lot of the material I presented today. So thank you very much, and I'll be happy for your questions.
Thanks, Alexander. Lots of good stuff today. So as we've mentioned before, there's a Q&A button over the bottom of your Zoom webinar interface, and you can just type in questions there. And we do have quite a few in there already, so we're just going to jump right in. The first one was, if my input current is chopped, it's a triangle DCM operation, but the envelope follows the voltage and THD is 10% till 2500 hertz. Can I say the PF is more than 0.98?
That's a tough one. I'd like to answer that afterwards to not do the wrong calculations in my head, if that's okay.
No problem. We will move on to the next one. That was a pretty technical one, but as I think I mentioned on the last one, we have all of these captured and we'll send out an email with some of these answers as well. Next one was, how many seconds is the appropriate transient time at startup?
So basically, there is no real rule of thumb because this all depends on your power up behavior at all. So if you'd like to switch on everything quite fast in your design, you'll have the need for getting high amount of current from your grid or your supply. So if you think about a mains connection, this might not be such a huge issue, but if you'll think about a battery powered device, the battery will provide you a maximum current. So it's not that you're stating, okay, this is a fixed amount of time. It's the other way around. You'll have to ensure under all circumstances that your sequencing leads to a maximum current which not exceeds the capabilities of your source. And that's why this is not quite something I could answer with. It's always 10 microseconds. It strongly depends on your needs afterwards, and this has to be ensured in the cycling. It's a cycling definition itself.
Okay, and I'm not sure if this was a follow-up question, but I think it was. What is the standard between fast and slow?
Sorry, I did not get the relation right now.
Yeah,
Maybe we'll find it out in the recording later on, on
yeah,
that more on what this question targets to.
sounds good. What is the right way to measure the emissions of the switching node and input circuit of an SMPS?
So uh, we'll have to differentiate in that way. Um, if you're doing the analysis in general about the switching behavior, um, you could use any instrument in that way because you'd like to see the spectrum. You'd like to see if the switching happens to the right timing, and major target will be to not destroy your device at the end. So that's the first thing. I always, like mentioned in my last comment, emphasize that you're activating the FFT function. So you're using the same setup to do a pre-qualification if only these components, so this the switching frequency itself, occurs, and also the harmonics related to the switching frequency generation, which will be more or less rectangular jumps you're having there. As soon as we are going for the system behavior, we are looking only at the input and output voltages and currents. So using there maybe a listen, so a line impedance stabilization network, maybe also a dual listen, so taking the coupling from the P and the N. So the cool thing with using a dual listen will be that you immediately see the common mode and the differential mode noise. And then you could easily see if your filters you positioned at the outsides of your switch mode power supply are operating sufficiently and as intended. Um, this will all be something you could do at your bench, and this would be called then pre-compliance analysis. If we're then pushing that on a higher level, then you'll need to be more close to the standards. So then you'll have the definition from the EMI standards, how the setup should look like. You'll need a shielded chamber and so forth. So it could become quite fast, quite complicated and expensive, because then you'll need at a certain point the measurement receivers, as well as the standard approved listens, and of course the EMI receiver at the end for taking then from the listen or from the antenna these signals. For everything you could do at the bench, typically you're good to go with a listen, so it could also be a custom listen, a ground plane where the listen and the DUT have the same reference at least, and also using a near-field probe to correlate the noise you see with the portions of your device. So you could see what's happening at the inductors, what's happening across your switching devices, and maybe also see, okay, if a ground loop or something occurs which is radiating or resonating, you'll easily find that also later on with a near-field probe set. So for everything you could do at the bench with low effort, low cost, a near-field probe set, a self-built dual listen would be recommended. But that's again not 100% then correlated to your EMI measurements. It's only giving you an indication if you're better with these certain countermeasures or if you'll have to do further investigations here. Sorry for the long answer.
Very, very comprehensive. The next one, what is your recommended way to measure inductor current?
So here the inductor current would follow my recommendation previously. I would always prefer to use a shunt and then use a differential probe over that shunt because it's the most accurate and broadband measurement you could get right now. Of course, you'll have to decide if you'd like to do a measurement then current correct or voltage correct. So the efficiency has to be done in 2 steps. If you'd like to do these investigations on the losses, you'll have to decide if you're now measuring the current in the inductor or the voltage there, because both measurements will affect each other in a way that you'll have to decide which one to take first and then the second.
Thank you. Next up, what recommendations are there for measuring low current, like milliamps and UA for battery powered devices?
Yes, so for these IoT devices, we'll have sleep currents in the microampere range going up to milliampere. If we're only going through these 3 dimensions from micro to milli, this might be okay to use averaging and so forth, because typically these currents don't change that fast. So there are solutions with more than 8-bit available on the market. So you could use, rather than your MX04, with a 12-bit ADC, also using low-pass filtering to get rid of wideband noise of your front band and so forth. For the RTO platform, we are having an additional box which provides you about 1 megahertz of bandwidth, the so-called RT minus ZVC, and therefore with a 12-bit ADC, which will give you sufficient dynamic range. So that's a more or less sophisticated task, and that would be also something to discuss in a follow-up. What would be the right solution? in dependency of what else should be done. Because typically it's not only sleep and wake up current you'd like to see, also maybe you'd be interested in doing some controller measurements, seeing what's happening there.
Thank you. Little non. Can you put the link of the testing manual that you showed in the laser slide? Is that something we can easily get out to them, Alexander?
Yes, of course. We'll provide that afterwards with the slides.
Great. Next one. What about using the coaxial cable without a DC block? What termination do I need to use on the scope? 1 mega ohm or 50 ohm? If using a 1 mega ohm termination, is that an issue?
Um, I guess that targets to the slide with the different probes. So the 10 by 1 by 1 probe. If you just connect immediately the front end of the oscilloscope with a coaxial cable to your DUT, you'll have to ensure that the capacitive load you're adding to your DUT is okay for your switch mode power supply or the line you'd like to investigate. Um, the choice of 50 ohm or 1 meg ohm primarily is depending on the voltage level. So for 50 ohm, you shall not exceed typically for the scopes we're talking in this presentation about of about plus minus 5 volt. If you're exceeding that, you have anyhow no chance to not use 1 meg ohm. But with a 1 meg ohm, you'll have to be aware that you no longer have a non-reflective termination at the end of the cable. So your excitation at the beginning of the cable will travel to your front end and then back to your device. And this could maybe cause you, in worst case scenario, an constructive interference at your testing point, which leads to an overvoltage at your device and might lead to destruction there. So I would not recommend to directly connect the front end itself due to loading and these resonance effects. If you might want to use 1 meg ohm termination at the input of the scope, and you'll have the chance to design your own 50 ohm termination, which could handle the max voltage. Then you could do it like for the older Ethernet standards. You'll have the termination at the end of your line, and in parallel with a T, you'll have a 1 meg ohm input of the scope measuring the signals. So that would be possible, but only for lower frequencies in the range up to 1 or 10 megahertz as a maximum. Above, the reflections and the terminations get such imperfect that this would cause more distortions when using an active probe.
Okay, thank you. When computing switching losses, should the time be set as high as possible?
Um, that's also a pure yes and no, because if you did not do the de-skewing upfront, you could take your measurement time as long as you'd like to, you will always get an error. Um, Basically, the first thing to know is you could do the loss calculation even in a one shot with a single acquisition over one pulse. This would give you a bad statistic on your device. But if you have disqueued everything properly and your device is statistically behaving nicely, then you see immediately the correct losses. Typically, I would recommend to first of all do the disqueue and afterwards let the measurement run over a certain amount of time to see if maybe also heating changes the behavior and the losses due to parasitic effects like thermal coefficients and so forth.
Thank you. Should overshoot or undershoot be measured from initial voltage or final voltage after transient?
That's always on a good one because these definitions are typically made by standards or the data sheets, how these shall be measured. Um, I've seen everything, so I cannot give a direct recommendation to do it always in one manner. Um, what you shall be keeping in mind though is the over and undershoot might not always be a pure function of your system. So this is also depending on the input front end characteristic. And thus this might cause differences in your measurement when using different measurement devices. So here, sometimes it's helpful if you're uncertain if it's the measurement system itself or not, to exchange the probe. If you'll have two different probes that could be capable for this measurement, or maybe also to use another scope, or if you're comparing two colleagues, to ensure at least that you first of all did the measurements with the same thresholds. So like this 1090, 2080 discussion I made in the presentation. And of course, also to know if these automatic measurements, if you're using that inside the scope, are referencing then also to the high, the absolute peak, the mean, or the low values. These could be typically adjusted, and these are also typical errors. So it's very important to document also if you have made some changes to these definitions, which you have done, and to align on that. Otherwise, reproducibility of measurement results will be impossible. So if you'll get these things from your colleagues without any statements, please always ask, with which settings did you do these measurements?
Great. Next one, could you please repeat, what is the challenge to measure the high side FET regarding common mode rejection?
Um, the challenge always is that all probes have a somehow limited common mode rejection. So the common mode rejection ratio gives you the influence if you're taking the same test point for the P and N input of your probe. Then you'll have a floating potential due to the switching of the high side transistor. And then you'll get a certain ripple at the output of the probe stated. And let's assume you'll have 1 kilovolt, you'll have about 30 dB of attenuation in between. You'll get a resulting ripple out of, 60 dB of attenuation in between. This would give you immediately a factor of 1000 of attenuation. So from 1 kilovolt, 1 volt of amplitude would be left. And this one is frequency depending. So you will always have to know which frequency range you are in. And then you could check the data sheet with the given common mode rejection plots there and do an assumption how large would be the resulting voltage. And below that value, you can no longer qualify the output ripple because you don't know if it's coming from the switching or if it's a real ripple behavior of your system. So it's just a matter of identifying what will be the real measurement value.
Okay. Back to the inductor. Is it better to measure the inductor current before or after the inductor?
That's also a tough one. Typically, I'll measure the inductor current at the output because that's the consumed current from the DUT typically. Um, if you'd like to do the analysis on the mains connection, then you would measure it up front. So it all depends on which way the energy shall flow or which energy flow you'd like to characterize.
All right. So I think we are going to end up in the same boat as the first session with lots of great questions and not quite enough time